If we talk about linear algebra as the language of artificial intelligence, first we will discuss why study linear algebra today. See, the modern world, it runs on data, and linear algebra is the math of data. If we talk about linear algebra, it is the math of data. Linear algebra provides the essential language for representing multidimensional information and the computational framework for processing data at scale. So now it's very clear to us that in the modern world, we are dealing with the data and we need some mathematical tools so that we can efficiently handle that data. We can represent that data. We can process that data in an efficient manner. And linear algebra is that tool. So linear algebra is that tool using which we can represent multi-dimensional information. And linear algebra, it also provides us the computational framework for processing data at scale. So now we are getting or we are realizing the significance of linear algebra, especially how it is a perfect tool in dealing with data, in processing data, in managing data. So every major technology today, it depends on linear algebra. So any major technology you take, it has something to do with the linear algebra. Like if I talk about artificial intelligence, machine learning, deep learning, so these all, they make use of linear algebra. So artificial intelligence, machine learning, deep learning. So linear algebra is the bedrock of artificial intelligence, machine learning, deep learning. And linear algebra, it is used from data storage to actual learning process. So in the field of AI, ML, and deep learning, we use linear algebra to represent the data. We use it for data representation. So all the different forms of data, like the images, text, audio, it is converted into vectors, that is the list of features, and matrices, that's the data sets for computers to process. So in AI, ML, and deep learning, whatever the data we have, that data can be the text data, textual data, images, audio, we convert that data into vectors and matrices, and then we compute it. So, if we are talking about vectors and matrices, we are talking about linear algebra. So linear algebra is used for data representation in AI, ML, and deep learning. And similarly, linear algebra is used for model training. So in neural networks, learning involves repeatedly multiplying input vectors by large weight matrices. And that multiplication of input vectors by large weight matrices is carried out using the principles of linear algebra. And hence, linear algebra plays a role in model training. So the idea is that we have a data, like the input data, we have the weight matrix. Now using the principles of linear algebra, we multiply the data, the input vector with the weight matrix to get some prediction vector. So we carry out the matrix multiplication, which is a concept of linear algebra. Linear algebra, it is also used in AI, ML, and deep learning for optimization. So optimization is like minimizing the cost function, minimizing the error. So techniques like gradient descent, it uses linear algebra to adjust weights, minimizing errors, and improving the model accuracy. So now it's very clear that in the field of artificial intelligence, machine learning, and deep learning, linear algebra plays a very, very important role. Linear algebra is used to represent the data, whether you are dealing with the textual data, you're dealing with images, or you're dealing with audio. We convert those data into vectors and matrices before further processing it. So linear algebra has a role to play in data representation. In the field of AI, machine learning and deep learning, linear algebra plays a role in model training. So we multiply the input vector with the weight matrices. So that matrix multiplication is taken care by the principles, the concepts of linear algebra. And also linear algebra also plays a role in optimization. Like in AI, ML, and deep learning, we use gradient descent as one of the optimization technique. And that gradient uses gradient descent. It makes use of linear algebra to adjust weights, minimize errors, and improve the model accuracy. So linear algebra, it also plays a role in recommendation systems and search engines. So linear algebra is used in recommendation systems and search engines. So modern web platforms, they rely on matrix operations to organize the internet and predict what you will like. So in search engines, matrix operations are used. In recommendation systems, operations are used. So if we talk about search engines, and in search engine also, uh, we are mainly emphasizing on the page rank. So in search engines, especially the page rank, Google, it represents the web as a massive adjacency matrix where links between pages are entries. So companies like Google, like we all use Google search. So Google search, it represents the web as a massive adjacency matrix wherein the entries of these matrices is the link between these web pages. So finding the most important pages is mathematically equivalent to finding the dominant eigenvector of this matrix. So Google search or any search engine you consider, if we are talking about the page rank algorithm of Google search, it makes use of the adjacency matrix to represent the web pages. So the entries of adjacency matrix is the links. So wherever there is a link between the web pages, that will be an entry in the adjacency matrix. And we find the most important pages mathematically using the linear algebra using the concept of eigenvector. We find the eigenvector of this adjacency matrix, which will give us the most important pages. And hence we are making use of linear algebra here. Similarly, in recommendation systems also, we make use of linear algebra. So recommendation systems, you know that we have seen recommendation engines like any e-commerce platform. If you visit, it recommends you some products. If you explore an OTT platform like Netflix, it recommends you movies. If you visit LinkedIn, it will recommend you connections to follow. So that is what recommendation engine is. So in recommendation systems, like services like the Netflix, it uses collaborative filtering. So companies like or the products like the Netflix OTT platform which we use, it makes use of the collaborative filtering, which involves factorizing a large user item matrix into small feature matrices to predict missing ratings. So this is called as matrix factorization. So basically in collaborative filtering, Netflix, what it does is that it uses the user item matrix, like based on the past behavior of the user, what items the user preferred. So making use of the user item matrix, it factorizes a large user item matrix into two smaller feature matrices. So these are like the feature matrices. So we have a matrix called user feature and an item feature. So a large user item matrix is factorized into a user feature matrix, a smaller user feature matrix, and a smaller item features to predict the missing ratings. And here also we are making use of matrices, and hence we are making use of linear algebra. So now we are realizing the importance of linear algebra, that linear algebra not only in artificial intelligence but also in recommendation systems and search engines, linear algebra plays a very big role. Similarly, linear algebra do play a role in computer vision and robotics. In computer vision and robotics, linear algebra plays a very big role. So computer vision and robotics, they use linear algebra to translate physical word geometry into digital coordinates. So if I talk about computer vision in particular, so in computer vision, digital images are stored as matrices of pixel values. So in computer vision, we represent digital images as matrices of pixel values. Operations like the edge detection, blurring, or rotating are performed by applying linear transformations, that is a matrix multiplication, to these pixels. So the operations on the image is basically the linear transformations of these matrices. So the idea is that in computer vision, we represent digital images as matrices, like we represent it as a pixel matrix, a matrix containing the pixels. And the operations on these images, like the edge detection, blurring, and rotating, is basically the linear transformations on these pixel matrices. So, hence, computer vision heavily makes use of linear algebra, because whenever we are talking about matrices, we are talking about linear transformations, we are talking about linear algebra. So linear algebra is used to represent digital images and also to process digital images. Similarly, in robotics, if we talk about robotics, in robotics, engineers they use homogeneous transformation matrices to model a robot's pose, that is a position and orientation. So the modeling of a pose of a robot is done using homogeneous transformation matrices, which is a concept of linear algebra. Even like solving inverse kinematics, like calculating how joints must move to reach a specific point, is a complex system of linear equations. So in inverse kinematics also, it involves complex systems of linear equations, which is a part of linear algebra. So now it's very clear that if we talk about linear algebra, it has applications in computer vision and robotics. In computer vision, we represent digital images in the form of matrices, pixel matrices, and processing of image is basically the linear transformations performed on the pixel matrices. Similarly, in robotics, we use homogeneous transformation matrices to model a robot's pose, and to solve inverse kinematics, we make use of complex systems of linear equations, which is a part of linear algebra. So linear algebra, it also has a role to play in scientific computing, signal processing, and beyond. So linear algebra do have a role to play in scientific computing, signal processing, and beyond. So linear algebra provides the heavy lifting for complex simulations and data analysis. So if we talk about scientific computing, if we talk about scientific computing, so linear algebra plays a role in simulating physical phenomena. So simulating physical phenomena like the weather, fluid dynamics, it requires solving millions of simultaneous linear equations, often using LU or QR decomposition for efficiency. And which are the concepts of linear algebra? So linear algebra, it is used in scientific computing. So when we are simulating physical phenomena like the fluid dynamics, weather, it requires solving millions of simultaneous linear equations. And to solve those millions of simultaneous linear equations, we make use of the concepts of linear algebra like the LU or QR decompositions. Linear algebra also has a role to play in signal processing. So in signal processing, techniques like the fast Fourier transforms, which is also used in Wi-Fi and audio compression, are rooted in linear transformations that convert signals between time and frequency domains. So, if we talk about signal processing, in signal processing, converting the time domain into the frequency domain and vice versa is very important. So, the fast Fourier transforms, they make use of linear transformations, which is a concept of linear algebra. So, linear algebra do play a role in signal processing also. So, the fast Fourier transforms, like conversion from a time domain to frequency domain, it makes use of linear transformations. And linear algebra also plays a role in dimensionality reduction. So principal component analysis, it uses eigenvalues and eigenvectors to compress high dimensional data, keeping only the most important features. So the idea is that, let us suppose we have some high dimensional data. Now using the principal component analysis, like which makes use of the eigenvalues and the eigenvectors, so we can reduce the dimension. So, so dimensionality reduction we can do using the principal component analysis, which further makes use of eigenvalues and eigenvectors, which is a concept of linear algebra. So now it's very clear to us that, okay, if we talk about scientific computing, signal processing, and beyond, like dimensionality reduction, linear algebra plays a role. In scientific computing, like if we are simulating physical processes, it involves solving millions of simultaneous linear equations. We make use of the concepts of linear algebra, like the LU or the QR decompositions. In signal processing, we do the conversion of the time domain to the frequency domain. We make use of something called as fast Fourier transforms. It uses linear transformations, which is a part of linear algebra. And also in dimensional reduction, we make use of principal component analysis, which uses eigenvalues and eigenvectors to compress high dimensional data into important features. So this eigenvalues and eigenvectors is a concept of linear algebra. So linear algebra is the hidden engine behind AI. Linear algebra is the hidden engine behind AI. So if we look at like what powers the modern AI, data as geometry. So in the world of AI, data isn't treated as text or images. It is treated as geometry. Because you know that in artificial intelligence, we try to find the patterns in the data. And if we are trying to find the patterns in the data, we are considering data, or we are treating the data as geometry and not as text or images. So in the world of AI, we treat data as geometry to identify patterns in it. So that is what is the core philosophy behind the modern AI, finding patterns in the data. So if we treat data as geometry, it is possible for us to find the patterns. And to treat data as geometry, linear algebra plays the role. So linear algebra is the framework that allows computers to see patterns in high dimensional space. So we can see patterns in high dimensional space using linear algebra. Linear algebra is the framework. So if we talk about the core components of linear algebra, which powers the modern AI. So the core components is the how. So we have vectors. So vectors are the basic building blocks. Every piece of data, like a word, a pixel, or a user preference, is converted into a vector. So vector, you can treat it like a list of numbers. Now that list can be a horizontal list or a vertical list. So we can have a row vector, we can have a column vector. So list of numbers is a vector. So basically, whether we are talking about a word, a pixel, or a user preference, like every piece of data is converted into a vector. So this places the data at a specific point in multidimensional embedding space. where similar items are mathematically closer. So what we do, if we represent the data in form of vectors, then in a multi-dimensional embedding space, automatically we will see that the items which are related to each other, which are closer to each other, mathematically also they will be close. Like let us suppose if we have data related to dog, so it will by default be occupying, it will be close in this region, and the data points related to cat will be falling in this region. So if we represent the data as vectors, then because of that, automatically the vectors in a multidimensional embedding space, similar items, they will fall closer. They will be mathematically closer to each other. And hence, this is a very powerful concept which enables us to find patterns. And now, see, we already saw that with linear algebra as a frame. So, linear algebra is the framework to represent data as geometry. And now we are getting a feel of it. Because if we represent the data as vectors, by default, similar items, they will be mathematically closer to each other. So, we are treating data as geometry. So if we talk about the core components of linear algebra, we have matrices. So the core components of linear algebra which powers the modern AI, matrices is one of the core component. So you can think of matrices as the memory of the AI, the AI's memory. A matrix is a collection of vectors. And since it's a collection of vectors, matrix represents a data set. In a neural network, the weight matrix stores everything the model has learned. So in neural networks, we may use of something called as the weight matrix, which represents everything which the model has learned. So weight matrix stores the learned information. So when you input data, it interacts with these weights. So input data interacts with these weights in the weight matrix. Now the next core component of linear algebra powering the modern AI is the transformations. So see, vectors and matrices, it is more of like representation. Vectors and matrices, they are used to represent the data, but transformation is the action, processing the data. When an input vector is multiplied by a weight matrix, it undergoes a linear transformation. So whenever we multiply a input vector with a weight matrix, then the result is a linear transformation, and that transformation can be rotation, scaling, shearing, and this allows this transformations allows the AI to filter out noise and highlight relevant features. So whenever we perform operations on the vectors and matrices, whenever we perform operations, we are basically performing the linear transformations. And with this linear transformations, we can filter out the noise, we can highlight the relevant features, and so on. We also have a core component called optimizations. So optimization is also a core component of linear algebra which powers the modern AI. So see, AI, it learns by minimizing the error. Artificial intelligence, it learns by minimizing the error. So optimization makes use of calculus plus linear algebra. So by calculating the gradients, the system exactly determines how to nudge the numbers in a matrix to make the output more accurate. So that is what the gradient descent is, which is an example of a optimization technique which makes use of both the calculus and the linear algebra. So linear algebra also plays a role in optimization. So by calculating the gradients, we can find like how exactly we should update the numbers in the weight matrix to make the output more accurate. So if we talk about the core components of linear algebra, so eigenvalues and eigenvectors is also a core component of linear algebra which powers the modern AI. Eigenvalues and eigenvectors. So eigenvalues and eigenvectors, they identify essential directions in data. They tell the AI which features are the most important. They show most important features. For example, if we talk about facial recognition, eigenvectors are basically the eigenfaces, represent the most distinct features that separate one face from another. So eigenvalues and eigenvectors are like some very powerful components of linear algebra. They identify essential directions. They show the most important features to consider. Like if I talk about facial recognition, in a face, we can have so many features. But if we make use of eigenvectors, then we will have eigenfaces. So eigenfaces are the faces containing only the most relevant features, eliminating all the noise, all the unnecessary features, we are getting rid of it. So that is what eigenface. And eigenface, we can get it using the eigenvectors. Similarly, singular values, like singular value decomposition, is also a core component of linear algebra which powers the modern AI. So this is the ultimate tool for compression and noise reduction. So if you're talking about compression and noise reduction, then singular value decomposition is the ultimate tool. Singular value decomposition allows a system to take a messy matrix and break it down into its most important parts, discarding the junk data without losing the core information. So singular value decomposition, it's a technique of linear algebra which breaks down a messy matrix, discarding the junk data and keeping the core information. So now we looked at the core components of linear algebra. Now we will look at the functional benefits of linear algebra, the why. Like why we should use linear algebra, or why linear algebra is powering the modern AI. The functional benefits of the linear algebra, like why we should use linear algebra, or why the linear algebra is powering the modern AI. So representation. So linear algebra provides a universal language. Whether you are translating French to English or identifying cancer in a X-ray, so whether you're translating, identifying, doing some kind of a recognition, linear algebra represents both problems as operations on numerical arrays. So linear algebra provides a universal language for representing the data. So regardless of the operation you are performing, if you represent the data in the form of vectors and matrices, you can solve problems. So that is what the linear algebra is. So now it's very clear that why linear algebra powers the modern AI, because linear algebra provides the universal language to represent the data. Computation. If we talk about modern hardware like the GPUs, they're specifically designed to do one thing extremely well, that is the matrix multiplication. So modern hardware, they make use of like GPUs. So GPUs are designed for matrix multiplication. GPUs are designed to carry out billions of simultaneous calculations. So linear algebra allows us to perform billions of calculations simultaneously rather than one by one. So now it's very clear to us that linear algebra, why it powers the modern AI, because it provides the universal language to represent the data. It provides the computational framework, because modern hardware like the GPUs, they make use of linear algebra, they make use of matrix multiplication to carry out billions of simultaneous calculations. Structure. So linear algebra, it turns chaotic data, unstructured data into a rigid geometric grid. Because with linear algebra, we are treating data as geometry. So linear algebra, if we represent the data using the concepts of linear algebra, then we are turning the chaotic unstructured data into a geometric grid. This structure allows us to use concepts like distance and angle to find invili- relationships between data points that would be invisible to human eyes. So once we convert the chaotic unstructured data into a geometric grid, we can use concepts like distances and angles to find the invisible relationships between the data points. And this is how the linear algebra is powering the modern AI. And also, we have efficiency. So, techniques like dimensionality reduction using SVD, PCA, like singular value decomposition, or the principal component analysis, it allows the AI to process massive data sets by focusing only on the components that matter, drastically reducing the amount of memory and power required. So, dimensionality reduction is also a concept of linear algebra. So, with linear algebra, we can also achieve efficiency, wherein we can process massive data sets by drastically reducing the amount of memory and power required. So, now it's very clear to us that why linear algebra is powering the modern AI. Linear algebra provides the universal language to represent the data. It provides the computational framework like the matrix multiplication, using which modern hardware like the GPUs can carry out billions of simultaneous calculations. Linear algebra provides structure, like it can turn a chaotic unstructured data into a geometric grid structured data. Using linear algebra, we can treat data as geometry, which allows concepts like distance and angle to find invisible relationships between the data points. And linear algebra, it also provides efficiency, wherein we can use the concepts of dimensionality reduction to process massive data sets using reduced memory and power consumption. And hence, linear algebra is the hidden engine behind artificial intelligence. Linear algebra is the language of data. Data is naturally matrix shaped. See, in the modern digital landscape, data isn't just stored in tables, it is mathematically defined by its arrangement. This matrix shaped nature of data allows computers to apply mathematical operations to real world concepts. Let us look at some examples to get a feel of it, like how data is naturally matrix shaped. Let us try to understand it. So, if we talk about student marks, so we can represent student marks in the form of a matrix. So, rows will be the students and columns will be the subjects. Like student 1, maths, physics, chemistry. So, columns will be the subject, subject 1, subject 2, subject 3, and rows will be the student. So, we can represent the student marks in the form of matrix. Similarly, if we talk about images, the pixel matrix, the pixel intensity matrix is a matrix representation of an image. If I talk about Netflix recommendations, we can represent Netflix recommendations using something called as user item matrix. User item matrix. We can represent neural networks in the form of weight matrices, and social networks we can represent using something called as graph adjacency matrices. So now it's very clear that data is naturally matrix shaped. Any sort of problem you talk about, you can represent it in the form of matrix. Now all these we can discuss in some more detail. If I talk about student performance, which is a tabular data. So we already saw that. So here the problem is managing and comparing academic performance of thousands of students across multiple subjects. Just imagine we are considering a college containing thousands of students. So now the problem is to manage and compare academic performance of thousands of students across multiple subjects. And here the matrix can solve the problem. So we can have a M cross N matrix where rows represent the individual students and the column represents the subject. And what advantage we get if we use this matrix to, to find the average grade for a subject, perform an operation on the column vector. To find a student's GPA, operate on a row vector. So in this matrix, the row vector will give us the performance of a particular student and the column vector will give us the performance of the entire college for a particular subject. So that can be a very powerful tool. Similarly, if we talk about digital images, the visual data, now the problem is computers, they don't see shapes. They can read numbers. Because computers, if you talk about, they can only understand numbers. They cannot see shapes and all. So we need a way to represent images in the form of numbers. And we have pixel matrix, pixel intensity matrix. So a grayscale image is a single matrix with pixel intensities 0 to 255. A color image is a 3D tensor. So it is a stacked matrix. So we will be having a 3D tensor, a three stacked matrices for red, green, and blue. So now it's very clear that we can represent a image in the form of a matrix. If it is a grayscale image, one matrix is enough. And if it is a color image, we have to use a 3D tensor. So three matrices we stack on top of it. Like we have a matrix for the red, for the green, and for the blue. And why it works? Applying a filter like in Instagram or Photoshop is mathematically multiplying the image matrix by a smaller kernel matrix. So now with this image matrix, we can perform operations on it. To process the image, we should process the matrix. So if we talk about Netflix recommendation or Amazon recommendation, we have user preference data. Now the problem is predicting what a user will like based on the past behavior and some other factors. Now if we make use of a massive user item matrix where rows are the users and columns are the items. It can be movies for Netflix or products for Amazon. Now, how this user item matrix can play a role in predicting what a user will like. So this user item matrix is a sparse matrix. Like in this, most cells are empty. So AI uses matrix factorization to fill in the blanks, identifying hidden patterns. We call it the latent factors, like prefers sci-fi movie, like science fiction movie, or 90s nostalgia. So if we represent the user preference data in the form of a matrix, like a user item matrix, then we can perform some matrix factorization, which can enable us to identify hidden patterns, the latent factors, using which we can recommend movies or the products to the users. So now we are getting a realization like linear algebra is the language of data. Like how if we represent the data in the form of matrix, we can make use of linear algebra to solve problems. Similarly, if we talk about neural networks, intelligence data. So in neural networks, the problem is how does a machine store the relationship between an input and an output? Because see, the idea is that in neural network, it is a supervised learning. In neural network, what we do is that we know both the input and the output. We know both the input and the output. We give input to the neural network and it learns the pattern. So neural network, what it does is that it learns the relationship between the input and the output. It predicts the unknown function which can transform our input to an output. So in neural network, we know both the input and the output. Neural network learns the relationship. Now the problem is how it will store the relationship. So to store the relationship, if we make use of the matrix, like the weight matrix, every connection between neurons in a model has a numerical weight. So if we assign a, so we know that every connection among the neurons has got a weight, a numerical weight. And if we store that weight in something called as weight matrix, our problem will be solved. And let us see how our problem will be solved. So see, processing information is essentially a long chain of matrix multiplications. This is why GPUs are so vital. They are built to multiply matrices incredibly fast. So if we represent the relationships in the form of weight matrix, then computation will be very efficient because GPUs, they are made for to carry out matrix multiplications, to carry out billions of operations simultaneously. And that is possible. And this is the reason, like if we talk about deep learning or the deep neural networks, there the weight matrix can be very big. But with GPU, we can for carry out billions of simultaneous operations. And this is where linear algebra is playing the role in neural networks. Social networks. So social networks, we are dealing with the connection data. Now the problem is mapping billions of relationships like the friends, followers, likes to see how information spreads. Now if this relationship we represent it in the form of an adjacency matrix, like if user A follows user B, cell A comma B is 1, otherwise it is 0. So that's the concept of adjacency matrix. So if we make use of the adjacency matrix to map the relationship, then what benefit we will get? Squaring the matrix tells you who is a friend of a friend. It turns sociology into a problem of graph theory and linear algebra. So the idea is that with matrix, if we represent the connection data of a social network in the form of an adjacency matrix, then using linear algebra, we can carry out certain interesting operations. We can square that adjacency matrix to get who is a friend of a friend. So we can turn sociology into a problem of graph theory and linear algebra. So now it's very clear that data is naturally matrix shaped. So if we represent the data in the form of a matrix, we can get some special benefits that we saw. So the key insight that we can take away from all this discussion we did, modern data problems are matrix problems. The modern data problems we are dealing with are basically the matrix problems. We no longer treat data as isolated snippet of information. By viewing the data as a matrix, we gain the ability to use linear transformations. We can rotate, scale, and project that data to find features that are otherwise invisible. If you can turn a problem into a matrix, you can solve it with a computer. So if we are talking about computation, if we are talking about GPU, then we have to treat the data as a matrix and not as a isolated snippet of information. If we can turn a problem into a matrix, we can solve it efficiently using a computer or a GPU. So modern data problems are matrix problems, and hence, if there is a matrix, there will be linear algebra. So we can say that modern data problems are problems of linear algebra. From numbers to data science, evolution of mathematical thinking. So if we talk about the evolution of mathematical thinking, it represents a shift from measuring objects to measuring relationships and finally to measuring entire systems. Because we started the mathematical journey by measuring objects. Then we started looking into measuring relationships. And now we are measuring the entire systems. So this progression is what allowed us to move from simple counting to building artificial intelligence. So if we talk about the evolution of mathematical thinking, it started with the step one, the numbers, the scalars. So it was all about measuring a single isolated quantity at a specific moment, like measuring the coordinates of a point in space or the temperature. Now, the limitation of this approach is that a single isolated quantity, a number, it has a magnitude but no direction or context. It is a point in a zero dimensional space because if we are talking about single isolated numbers, they are representing just the magnitude, no direction or context. For example, if I talk about the temperature is 32 degrees Celsius. So we are measuring the temperature with a single isolated quantity 32. Now this number is giving us an idea about how hot the object is, but it tells you nothing about the wind, humidity, or how the weather is changing. So that is what the number. So we started our mathematical journey, the mathematical thinking by measuring objects. And to measure objects, we just dealt with numbers, the scalars, single isolated quantities. Then we came across equations, the variables. So equation means dealing with the relationship between the numbers. So equations, the concept is the rule or the relationship between the quantities. So identifying a rule or a relationship between two or more quantities is what the equation is. Then we started measuring the relationships, the rule or the relationship between two or more quantities. Now the limitation of this step, the equations, is equations usually solve for a static unknown. They describe a balance like a scale. So for static scenarios, equations are well and good for static unknowns. But what if we are trying to analyze a dynamic system wherein the relationship is also changing? If the relationship is static, we can make use of equations to deal with it. But if the parameters are changing, then we will be needing something called as calculus. We have to measure the change. So at that time, there was no calculus. So that is the limitation of equations. It is good for solving static unknowns. So if the quantities are not changing with time, then equations are good. But if the quantities are changing with time, then these equations will no longer be valid. Like if we talk about an example, like 2x plus 3 is equals to 7. Let us say this is a linear equation. Now, in order to satisfy this, what should be the value of x? If x is 2, then this equation is satisfied. So we are discussing the evolution of mathematical thinking, and the step 3 in the evolution is the vectors. which are basically the list of numbers. Now let us understand the core concept of vectors. So grouping multiple related quantities into a single mathematical object. So the core concept of vector is basically grouping related quantities into a single mathematical object. This is where geometry enters the picture. This is where geometry enters the picture. So here we are treating data as geometry. Here we are talking about pattern. So in vector, what we do, we group related quantities into a single mathematical object. And what benefit we get is a vector represents state or direction in a multi-dimensional space. So if we talk about vectors, vectors contains numbers as well as it also represents a direction or a state in a multi-dimensional space. So that's the power of vector. So instead of just temperature, a weather station uses a vector. And if the weather station uses a vector, it will make use of a mathematical object like this, which will contain information about the temperature, the wind, the humidity. So that's the importance of vector. So now the idea is very clear that with vector, we can group related quantities into a single mathematical object. So here we have a weather information of a particular geographical coordinate. So rather than just specifying the temperature, we are making use of a vector which is holding the temperature, the humidity, and the wind. Now the weather is a single point in 3D space. So vector, so that is what the vector is. So now we can imagine or we can realize the evolution of mathematical thinking, like how we started with the numbers, the single isolated quantities, to vectors, which are group of related quantities, like grouping of related quantities into a single mathematical object. Then in this evolution, we have matrices or the grids. Now let us understand the concept of it. So collection of vectors is the matrices. So a matrix does not just show a state, rather it shows a transformation or an entire data set. So collection of vectors. So a vector is an information about a single point, but matrix can represent the entire region, wherein the column can be individual points. Or let us suppose if we talk about weekly weather. So what was the weather on Monday, Tuesday, Wednesday? So matrix can represent the entire information, the entire data set. And with matrix, we can see the relationship also, like how the trends, the temperature is changing with days. So that is what matrix. So matrix is basically collection of vectors. Now, if we talk about the power of matrix, like what advantage we get, if a vector is a snapshot, a matrix is a photo album or a map. So the idea is that vector you can treat it to be snapshots, and if we collect all that snapshots, the collection of all those snapshots will be a photo album, and that is what a matrix is. It allows us to perform linear transformations, such as rotating an image or projecting data from 3D down to 2D. Now, in this evolution of mathematical thinking, we have the step 5, that is the data science. So data science is the massive systems. So let us understand the concept first. So using matrices so large that they efficiently describe reality. So in data science, what we do is that we measure the entire systems. So we make use of massive matrices containing billions of rows and columns describing the reality. So in data science, we deal with massive matrices like huge data sets describing the reality. We process it to measure the entire systems. So data science is all about measuring the entire systems. measuring the reality, analyzing the massive systems. So we make use of massive matrices, massive data sets, huge data sets containing billions of rows and columns, which describes the reality. Now, what is the power of data science? Like what benefits we get? So data science is like linear algebra at scale. We stop looking at individual numbers and start looking at the topology, the shape of the data. If we talk about examples, so we have an interesting example of LLMs, large language models, for example, ChatGPT. So here, language as a matrix of word relationships. So large language models, they treat the entire human language as a matrix of word relationships. Similarly, if we talk about genomics, it represents the human genome as a matrix to identify disease markers. And if we talk about social physics, mapping every human connection on Earth to predict economic trends. So, when we talk about data science, we are talking about linear algebra at scale, wherein we are talking about huge data sets like large language model. It makes use of the entire human language. So, we have a matrix which is representing the entire human language, the word relationships of the entire human language. So, linear algebra at scale. And with this, we can measure the entire systems. We can analyze the entire systems. So now we can see the fundamental shift. Like we started our mathematical thinking by asking questions like what is the value, to asking question like what is a pattern. Because now in the modern world, mathematical thinking is not about measuring individual quantities. Rather, it is about measuring the entire system, analyzing the entire system. So now we are asking questions like what is the pattern rather than what is the value. And here, linear algebra plays a very big role. Linear algebra, it allows, so linear algebra is the only branch of mathematics that allows us to compute these patterns across millions of variables at once. So using linear algebra, we can compute patterns across millions of variables at once.